I've been struggling to visualize the idea of nothingness, you know, and obviously it all came to me. We know 30.8 billion years ago, the Big Bang, the universe happened, and so on and so on. So I've always been struggling to visualize what was it there before that, and I've been listening to Brian Greene about that, and Michio Kaku, and all these, sort of Brian Cox, all these physicists. And I would love to hear how you'd answer this question.
So you're asking how do we visualize what was before the Big Bang, or how do we visualize nothingness?
Yeah.
Well, I don't know what those guys would say, but the truth is that we don't know what was before the Big Bang, and it's a huge unanswered question. Some claim it's unanswerable. I would never go so far as to think that something is unanswerable, but I also don't really know how to. We don't really know how to answer this question. So it gets complex. It gets complicated by the fact that when you go back toward what we refer to as, I guess before the Big Bang, in fact, which was this inflationary period, right? Which of the universe is like, again, actually, if you look at it closely, like when you refer to the Big Bang, really what we're talking about is like technically the Big Bang itself happened after the inflationary period happened. And that's what the Big Bang is. But then when you put these things together, we have this thing called inflationary Big Bang theory. So it's kind of like the whole thing at the moment of, the inflation, et cetera. So again, I personally don't know how to visualize what happened before the Big Bang, because again, this gets complicated by the fact that because of our understanding of, like I said, things like quantum mechanics and quantum fields, when you get down to small enough length scales and time scales, and high enough energy scales, these are all equivalent, our current understanding of our current ability to describe things in a physically meaningful way breaks down. So for example, if we ask the question, what was before t equals 0, some people claim that there's no such thing as t equals 0, because once you get down below something like 10 to the power minus, what's the Planck time, 10 to the power minus 42 seconds or something like that. I don't know, something like that, but something enormously small. Once you get down to that level, the concept of time doesn't make any sense anymore. We don't have any kind of time step that you can physically describe as smaller than that. So if that's the case, then you have to logically conclude that there's no such thing as t equals 0. And, the expansion of the universe also followed as sort of like, it has sort of like been, I guess, eternal in a sense. But again, what this means is that it complicates our human understanding, to our human ability to describe such things. You know what I mean? So again, it's like, well, there's no intuitive understanding of this, because it might actually be beyond our current understanding of the universe. So maybe this seems like it's also evading the question, but this is just the kind of starting point to say that it might not be possible for us to really answer this question with our current understanding of the universe, right? So if quantum field theory is real, and it seems to be the way the universe works, and if our understanding of the Planck time and the Planck length are real, then we really can't say anything physically meaningful about times and length scales that are below those things and above energy scales like that. However, people start to go into more speculative territory, and they kind of like assume that, okay, they sort of say, okay, well, assuming that, because this is true, right? I mean, we know that, for example, we also don't know what's in the middle of a black hole, right? And behind all of this, behind a lot of the discussion that we're having and the discussion that people have about physics in general, the kind of ultimate edges of physics right now, is the question as to how gravity and quantum mechanics work together, which we currently don't know how this works. These work together. Maybe they don't, but that would be very dissatisfying to physicists. We like to have these mechanisms and explanations for how and why things happen the way they do. But the current place in the universe where these two theories come together, we suspect that they came together at some point back, far back toward the moment of the Big Bang. There was some kind of quantum gravity that existed. And the current place where these two things come together is in the center of a black hole, right? Because if you look at the equations of a black hole, it implies that they're at the center of the black hole, there's something called a singularity, which would be, some certain amount of mass within the zero volume or something, right? That doesn't make any sense, right? I mean, it mathematically makes no sense to have like a singularity. And so it's likely that the universe doesn't use singularities, which means that there's probably, and in fact, inevitably, there's some new kind of physical understanding that will step in both inside of a black hole and also back toward the moment of the Big Bang that we currently don't know what it is, those things could step in, and then eventually that will provide the piece that will allow us to understand, how to define what's before the Big Bang, or what was t equals 0, or what's in the middle of a black hole. So again, I'm taking the very, by contrast to the other people you talked about, right? I'm an experimentalist, right?
Yeah.
I guess Brian Cox started as an experimentalist too, but like, at the end of the day, I think that all these ideas are great. Again, we can talk about multiverse theory. We can talk about, infinite expansion, inflation. We can talk about all these kinds of things. But at the end of the day, I'm an experimentalist and I need some kind of evidence, right? I need somebody to show me. I think that we talked about earlier, you try not to get emotionally involved in any of your particular experiment or your theory, but we're also humans, right? I mean, if you see, if my theorist colleagues have like a set of math that's really elegant, that makes sense that they would get emotionally involved. And I was like, wow, this is really nice, right? Like string theory, again, Brian Greene is a good example. We talked about elegant universe earlier, right? It's like string theory is fantastically interesting, right? I mean, it's been mathematically very successful, and it does provide a really nice mechanism, a nice explanation for how gravity and quantum mechanics could work together. We currently have, and it's in principle it's testable, but we currently have no perceivable way of building a machine that would reach energies high enough to be able to test string theory directly. So as a result, it kind of like string theory has reached this realm of like this thing that's a really, really, really good idea that we can't test in the foreseeable future. That, of course, brings it, it gives it even more of a mystique for some people. They're like, whoa, well, it must be real because we can't get to it right now. It's like, okay, that's not the way science works. Again, as an experimentalist, I always have to go back to this. I need to experiment at some point to demonstrate this. But the speculative theories, I still think they're scientific. So, for example, if somebody, multiverse theory is a good example, right? Yeah. So if we, one of the ways that you might start to think about or visualize, what was before the Big Bang, you might think of some sort of like multiverse landscape of constantly inflating bubble universes that are constantly popping into existence in this enormous landscape of stuff. But when I say landscape, what does that even mean, right? Okay, what it sort of assumes that this landscape or these other universes, okay, they have to have something in common, right? They just can't be totally and completely different, right? I mean, for us to even postulate the existence of these other universes, you have to sort of assume that, okay, well, if there's a multiverse, it probably has some concept of space-time like ours does, because otherwise it makes no sense. Like it's just literally impossible to think about. Okay, so space-time exists in this landscape. Okay, that's fine. So then maybe these other universes also have space-time properties. Maybe you could squint and maybe like some of those properties are a little bit different from the ones that we have in our universe. But again, there's still going to be some shared notion of space-time. Maybe the dimensions of space are more. Maybe other people have tried to postulate the notions of like other dimensions of time. That doesn't make any sense to humans at all. So this is kind of a long version of saying that to try to visualize this is very hard. And for me, like I kind of like to think about the notion that we have this enormous landscape of possible universes in a possible multiverse. But what I'm saying is that this is a version where we have to sort of like, it again, what requires us to sort of change our brain and our mindset. Really what we're saying when someone says, multiverse theory is a possibility, they're kind of, in a sense, what we're doing is they're sort of changing what our attitude about the universe is, right? If you go back to the concept of the universe, even from a philosophical perspective, the universe was defined as everything that exists, everything that is in existence, right? Okay, so if we then postulate that we have this little bubble thing that we refer to as our universe, but then there could be other universes in a multiverse, well, that sort of expands the conception of everything that exists, right? So again, this is the long version of saying that this is hard for me to visualize. Yeah. And if I think about, but there's a real sort of visualization here that I find fascinating, is that, one of the, irrespective of, say, string theory or something like that, a lot of people are studying the notion that, one of the ways that our universe could have begun could have been as a seed, a sort of like a seed universe that branched off from another universe in the multiverse in a black hole in another universe.
Whoa.
And this sounds like science fiction that somebody would just write as a sort of weird thing that's sort of nonsense if you look into science, but this is entirely possible. And it comes from a lot of different perspectives. Number one, that we don't know what happens inside of the center of a black hole. Number two, the sort of, the kind of like interstellar version of like, Einstein-Rosen bridges, these wormholes. Yeah, these could exist. We don't have any evidence that they do yet, but the mathematics show that they could exist in principle. And the other part is that, if you look closely at black holes, if you look closely at the concept of a black hole, really, if you take Einstein's equation, where does a black hole come from, right? The prediction came before the observation, right? So this is fascinating. It's like this weird object that fell out of the equations. If you look closely at the equations, you can determine what it takes to make a black hole out of anything, right? So if I want to make a black hole out of the sun, it shows you take your favorite textbook on gravity. I assume you have a textbook on gravity on a bedside table like I do. And then you take that and you find the black hole equation, and it'll tell you how small of a volume you have to pack something in to make a black hole out of it. So to make a black hole out of the sun, we need to pack the entire sun into a volume that goes around like the center part of London. Okay. And to make a black hole out of the earth, we need to pack the entire earth into a volume that's about the size of a blueberry. And so to make a black hole out of you, we'd have to pack you all into a volume, I think, that's smaller than the radius of a proton or something like that. So, you're safe. But you can do this with larger things too. So if we want to make a black hole, like I said, we can do this with the sun. We can do this with the solar system. We can do these other things. What if we wanted to make a black hole out of the observable universe? So you can do this calculation yourself. If I take all the stuff within the observable universe, and my astronomer colleagues are very good at estimating the amount of stuff in the observable universe, all the particles and all the dark matter and everything like that. And they're very good at estimating this. And you get a number, it's some enormously large number. Then you put that number into the equation that tells you how small of a volume you have to pack it in to make a black hole. That volume is already larger than the current observable universe.
Wow. Okay.
And so you start thinking, okay, well, maybe they got the mass wrong, right? Okay, maybe, astrophysics has, lots of error bars on, the numbers from astrophysics, right? Okay, so maybe they got the number wrong by half, right? And that's a huge error. So, okay, let's take it by half. You're still the universe. To make a black hole out of the observable universe, you'd still need to pack it into a volume that's already larger than the observable universe, which raises the question, do we live inside an enormous black hole? And this is bizarre. It doesn't make any sense, right? Because like we think about the science fiction versions of black holes, it's like, this enormous object that's sucking in everything. And, when you go inside, you have this like light show, and then you show up behind your daughter's bookshelf and you give her Morse code or something like that, right? It's like, okay, that's what we think of as black holes. But a black hole, when you have a large enough black hole, in fact, if you cross the event horizon, you wouldn't even notice anything had happened. In fact, if you have a large enough black hole, you could be inside the black hole and not really notice for a very long time. And so if you apply this to the black hole in the concept that we might live in a black hole, in an enormous black hole, you start to see how this could be possible. So for example, if I have a large enough black hole and in my spaceship, if I cross over the event horizon, what would my experience be?
Yeah.
So inside of a black hole, inside the event horizon, what my experience would be is that I would have this sort of like horizon. There would be an edge of there'd be an edge of my observable my existence that is right there, and it's always getting slightly larger because more things are coming into my view, right? Because I'm stuck in this black hole. There's this thing called the event horizon, which is sort of like the point of no return, and it's other things are slowly falling into the black hole, and so I can see them as they come in, but there's this edge beyond which I can't see anything, and no matter how quickly I were to travel, I would never be able to get there because inside of a black hole, space is flowing into the center of the black hole faster than the speed of light compared to some perspective outside of the black hole. That's what it means to have a black hole. Space itself has sort of like a stuffness. It can flow and it can bend, as we know from general relativity. So that's what the experience would be like inside of a black hole. Now, what's the experience of us here on Spaceship Earth, right? We have a horizon. This is the edge of the observable universe that we can observe with our telescopes, beyond which we know stuff must be there, but we can't see it. And it's slowly things are coming into our view as the light as the light that is out from those things outside of there has finally had time to reach us. So this horizon is slowly getting larger, and more things are coming in. But no matter how fast we ever travel, there's no way that we could ever get there, because, as you know, space is expanding, the universe is expanding. And as you get farther away from us, the faster it's expanding. There's no way for us to ever get to the edge of the observable universe. As a result, okay, it's possible that our entire universe is inside an enormous black hole.
Wow.
So that means if you want to start to one way, again, I'm not saying this is just speculation, right? Because at the end of the day, we need a test. We need some experiment to test this, to test this hypothesis. But one way you could envision what it would be like before the Big Bang in our Earth is that if you postulate that our entire universe was birthed from a little seed of a Big Bang that was inside of a Big Bang seed that was birthed from a black hole in another universe, or another universe in the multiverse, then you can start to visualize a bit how that would be. But the visualization part breaks down too, because again, then we still currently don't know what's at the center of a black hole. We don't know we don't know how the universe evades these singularities and how to visualize that. We also don't know what it means for these things to exist. If you're talking about the inflationary Big Bang theory itself, then that's a different beast, right? Because, we know that the universe, the notion that the universe is expanding comes from the fact that we see it, we observe this right now, and everything is moving apart from everything else in all directions. And this means that if you just, go backwards in time, if you run the YouTube slider of the universe backwards, eventually everything had to be packed into a tiny, dense little point that then started expanding. We know that, right before inflation, you had something tiny, small, and then this thing, the expansion of the universe, as you know, didn't just go in kind of like a gradual way, like someone really controlled blowing up a balloon really slowly, right? It didn't happen at all. It had these weird epics. Like the first expansion of the universe was really fast. It's called inflation, right? It's like pow, and then it slowed down, and it went at a sort of gradual rate for billions of years, fairly gradual rate. And then a few billion years ago from us now, it started to speed up. So we call these epochs or epochs of expansion. It had this crazy expansion, then a kind of slow one. And then a few billion years ago, it started to accelerate it again. And this is the thing that we see happening right now. So if you want to visualize that, that's okay. That's harder. That's easier to visualize because you just kind of squint your eyes. And it's like, I have this little thing that was packed, and then it started to expand, and then it kind of slowed down and went like this. But before the Big Bang, I don't know. And if these other guys are describing what's before the Big Bang, then they're truly into speculative territory here.